Swayam Prabha. Digital India. Educated India.
So in this lecture, I'll be talking about mechanical properties of solid polymers. So the overall objective is to look at what is the relationship between. So the idea is to look at how stress in the material and strain and then time. So how these three are correlated and for solid materials. And this is important because we want to use plastics for some mechanical applications. So one of the design requirement is to see whether this polymer has enough mechanical property to withstand or resist mechanical loads. Okay. So typically when we think about design requirements, we are thinking about long term stresses. Under what condition this material was prepared and what's the history of different loads that is being applied to polymeric materials, especially in the solid state, and what level of strains we are thinking about, and how long this product is supposed to function. Okay. So each property has, each material has a particular life, usable life for its function. So it's going to be working for 1 year or it's going to be working for 10 years. So that information is also necessary to design your products. And what kind of chemical environment it's going to be exposed? Is it going to be used under acidic conditions or is it going to be under alkaline conditions? What is the pH? How much moisture is going to be there? Is it going to be exposed to any sort of an organic vapor? So the chemical environment in which this product is going to be used is also relevant. And safety, how safe this material is, okay, to what extent we can use it so that we don't have any compromise on safety, and what is the range of temperatures. Okay. In the last few classes we were looking at thermal effects, right? The polymers are very sensitive to temperature, so they can melt, they can degrade. Then there is glass transition temperature. So at what temperature we use is very important, and with respect to that, where the Tg, where the degradation temperature, where the melting temperature, all that is relevant, right? So therefore when we say design requirement for a plastic or a solid polymer, we have to keep in mind of all these specifications: operating temperature range, safety considerations, what kind of chemical environment is going to be used, how long we want this product to be serving, what is the ranges of strains and stresses. Okay. Why we need all these things? Because we want to make sure that we have a safe design for load bearing parts. Okay. In many as we said, plastic is a material that has lightweight. It can also have good mechanical property. Okay. But at the same time, we have to keep our safety consideration in check, because too much load can be dangerous for this plastic. So we have to know what is a safe design for carrying any mechanical loads, and we want to predict service performance. Okay, how long this material can be usable, workable, functional. And then we will also be able to compare material of different kinds. Maybe let's say you want to make a product with a high density polyethylene. The same product you can make with polypropylene also, right? So you have different kind of material choice. So doing this kind of a stress strain relationship or in mechanical property allows you to compare two or many properties of materials. And finally, to test and then make sure the quality control specifications are met. Okay. So these are the larger objectives of why we should look at the stress strain time dependence for solid polymers, right? So I'm going to talk about some general class of mechanical properties related to polymeric materials. Same things we do for other materials like metals. For metals also we do stress strain behavior. If you want to construct any material out of steel or any iron based structures. So when we do polymer, we do this similar kind of mechanical testing. So here I am going to show one video. The audio quality is not very good, but it is shot in the just like 1 hour before. This is based on the UTM tensile testing machine that we have in our lab. Sometimes during the course you may be able to also do this kind of experiment. So let's watch this video. Maybe I'll just tell you. So he's making, so this is Dr. Hem Kumar, he's one of my postdoc. So you can see that he's making a polymer film, okay, a polymer strand, and there is a machine called a tensile testing machine. So he's going to just load this film between two fixtures. One is going to be stationary and the other one is going to move at a particular rate. So basically you're pulling, this is called a tensile testing. So you're basically pulling a film, keeping one end fixed, the other end is pulled, and then you're going to measure how much stress and how much strain is created in this material, okay. So you can see that he's loading one edge at the bottom and he's fixing it so that it is in place. So it's tightly secured at the bottom. And the top as well. So now he goes to this, there is a software that is connected to where you have to put some information. For example, he would say what is the length of the film, what is the thickness of the film. These things you can measure before you load the sample. So you give operating temperature, room temperature in this case, and then you basically start the machine. It's very easy to operate. Then this software will measure as this piston moves up, as this lever moves up, it will measure the stress versus strain curve. So I think he's going to look at what happens to this film as the top portion moves upward. So you can see that there is some sort of features coming up, some whitish marking comes up. You can see some holes are getting formed as you pull. And this hole becomes larger and larger, and you see there is a fracture here, more fractures. All the while the top one is keep moving. Then there is a rupture. The film basically breaks after you apply sufficient amount of load, okay. So now whatever that happened there, it is actually recorded in terms of stress versus strain. So you see this curve that initially the y-axis is stress and the x-axis is strain, and then initially there is some sort of a linear curve, and then you see there is a broad more like a ductile like behavior, and then at that point where it ruptures, the data stops, the film becomes unstable. So this is a rupture point. This is a rupture point here. And then after that, see, he says how to load, how to save the data, and so this, as you can see, this experiment is extremely simple. All you need to do is you have to make a sample of a given length, make sure the thickness is uniform, okay. It assumes that the thickness is uniform, and then you load this to this machine, and then it just pulls up, and then at every point it measures the stress and strain, okay. So if you do this experiment, this is what the kind of data you will see. Stress, which is basically the force per unit area, versus strain. The strain is measured as change in the length versus divided by the original length, okay. So it's written as delta L by L naught times 100. So in this case, as the film is getting elongated because of this tensile force, delta L is always positive because the length is increasing, and this is divided by the original length. So strain is a positive quantity here, expressed in terms of percentage, right. So strain is a dimensionless quantity and it is given in terms of percentage. Stress is denoted as sigma, mostly given in megapascal, sometimes in gigapascal. So mega means 10 power 6, giga means 10 power 9, pascal, as you know, is 1 Newton per meter square. So what is shown here is a schematic of a typical stress versus strain curve of a material. So you can see that initially you start the material somewhere here where strain is 0, stress is 0. Now the material is basically pulled, okay. So now as this material is pulled, the stress is generated and correspondingly the strain is measured. So you see there is a kind of a linear region which we call as a proportional limit. In this case, stress and strain are linear, they are proportional. We call them as a elastic region. This is because if I stop at this point, the material will actually come back to its original position, okay. So this elastic region can be very small, it can be very long depending upon the material type. So typically the initial portion of this stress versus strain curve would be a linear or proportional limit, which we call them as a elastic region, right. So that is going up to 0.1. So up to 0.1 is a linear limit. So after that, if you keep pulling further and further, then what happens is this material will undergo some sort of an yielding behavior. Yielding behavior means giving in. Okay, there's going to be a plastic deformation. The material will not come back to its original position anymore. Okay, it is undergoing some permanent change. So that the point that is shown here as 2 is called the yield point, and the stress corresponding to that yield point is called the yield stress. Okay, so beyond that point, the material will not come back to its original position. It is giving in for the imposed load, and then the material will be relaxing a little bit further, and then if you continue to do this, it will actually go through another point. It will go to something called the ultimate strength. That is a maximum load it can withstand, and if you try to pull further, that 0.5 is when you see a rupture point. Okay, in the previous video where I showed, you did not have all the features. It was linear in the beginning, and after some time it was elongating, it was like ductile, it was expanding, and then there was a suddenly there is a breakage point. Okay, because that is the nature of the polymer that he tested. If you change to another sample, okay, you will see a different kind of behavior. But in any stress strain curve, you are going to expect a linear limit, elastic region, or proportional limit. There may be a point of yield stress. It may be exhibiting or it may not be there, depending upon the material and kind. Some materials have yield point and the corresponding yield stress, and then there will be always something called an ultimate strength, okay, after which the material will break, rupture, and the film becomes unstable. Okay. So why this information is important is because it tells you up to what load you can use this material for. Okay. So plastic, as you know, we use them for packaging, we use it for some sort of mechanical support, which will have some sort of a load bearing abilities. So this will tell you to what extent we can use this material. Obviously you cannot put this material above this stress, it is going to rupture. Okay, but it will tell you what limit we can use this material for. So for any plastic material used for mechanical operation, the stress strain curve is utmost important. Okay, it tells you up to what limit it can withstand. So yield stress is kind of giving you another limit below which the material can undergo elastic deformation, but it can withstand its original shape and size. If you go beyond that yield point, it is going to be a plastic deformation, and up to 0.5 it's okay, and after this is going to rupture, right. And it also tells you up to what length you can actually, the strain basically tells you to what extent you are able to stretch it. Okay. So the strain at which it breaks is called elongation at break. The longer it is, you can keep on pulling. Okay. Some of the brittle material will have very short, short strain at which this breakage happens. Okay. So let me show you some more examples here. So each of this, so I am showing 5 curves here, each corresponds to different kinds of polymers. Okay. Again we are plotting stress versus strain. The first material shown by curve 1 is an example of a brittle polymer. Okay. What do we understand by brittleness of a polymer? What do we mean by brittle? When do we call a polymer as brittle? Huh? Co-yielding. No yielding. No yielding. But based on what we already learned, what is brittle means? What is a microstructure will look like for a brittle polymer? Cross-linked. Okay. What else? Cross-linked. Yeah, it could be a cross-linked polymer. Closely packed. So we expect glassy polymer or amorphous polymer typically being very brittle, whereas a crystalline polymer, semi-crystalline polymer would be more ductile, right. So here polystyrene is an atactic polystyrene, so it does not crystallize, it forms an amorphous glassy material, so it is going to break, it is going to be very brittle. So that is why you can see when you look at this stress versus strain for curve 1, the stress is very high, the stress is building up very rapidly as a strain is applied, and then it quickly breaks at some point of time here. Okay. So it basically breaks at a very small strain. So that means this material will have a very small elongation at break. It breaks at a very small extension itself, okay, but it can have very high strength because it's very stiff. So this can be one possibility. Some polymers which are glassy, which are amorphous, which are brittle will show this kind of a stress strain behavior. Okay, they are very stiff. It can actually withstand many high amount of load, but it will break beyond this point. There is no yield point at this point, right. So if you look at this point 2, the curve 2, this is an example of a ductile polymer, something like polycarbonate, or the one that is shown in the previous video, where there is an initial linear proportional limit, and after that it basically slowly gradually it yields. There is no sharp yielding point like the previous one, but it kind of it becomes more and more ductile. So it basically elongates very slowly. So maybe suppose if it drops here, this would be the elongation at break. This strain is going to be the elongation at break. So ductile polymer would have high elongation at break. That means you can stretch for a longer strain. So you can see that the flexible rubber like material shows 4. The difference between 2 and 4 is that you can see the magnitude of stress is more for 2 and less for 4. That means when you have a rubbery flexible rubber, they are going to have a very less amount of stress, but it can also show very gradually yielding or very ductile behavior. And case 5 is again a flexible rubber, but there is an additional process happening, what is called strain hardening. So when you keep pulling, when you apply the strain force, the chains can actually align and become very close packed, and we can become hardening. Okay, so that is called strain hardening, and that's why there is an upward trend in the stress strain behavior. Okay, and the curve 3 is more general, more a case where you have all the regions. There is a linear region, there is a clear yield point, and then there is a kind of a ductile region, and then there is a strain hardening also. Okay, so as a student you should be able to look at the stress strain curve. By looking at the shape, you should be able to tell whether there is a yield stress or not, whether there is a yield point or not, is there a strain hardening present or not, what extent the linear region is extending, where is the elongation at break. Elongation at break is a strain that corresponds to where the breakage happens. So for curve 1, this is the elongation at break. For curve 2, this is elongation at break, right. So that is what so kind of giving a summary of various possibilities for stress strain curve. Okay. So this stress strain curve is not very universal. Okay, as much as it depends on the different type of material, it can also depend a lot on temperature. It can also depend on at what rate this is strained. Okay, the straining rate can also change. For example, in this figure, we change the temperature, we increase the temperature in this direction. So here we have low temperature, and here we have high temperature. We are plotting stress versus strain, same polymer, same material, but the operation is conducted at different temperatures. So what you see is that as the temperature basically decreased, the line of failure, that is the breakage, the rupture point, keep increasing. That is because when you increase the temperature, you basically have more thermal motion, and the chains can actually relax much faster. Okay, so they actually can have higher elongation break, but you can see that the stress at which this breakage happens comes down. Okay, so it has a very strong temperature dependence. So here is so this is a very generic case. Here is an example. If you take polyvinyl chloride PVC, and you can see that these are the stress strain curves for temperature from -60 to +23, that is room temperature. Okay, so you can also see that as you increase the temperature, the yield stress comes down, and the elongation at break also changes. And here other parameter, which is called strain rate, the rate at which you pull, right, that strain rate is also changed. So here also you can see that when you increase the strain rate, you basically go to a shorter and shorter elongation at break. Okay, so the temperature is important, material is important, and the rate at which you are straining is also important, right. So so I think the temperature dependence is also shown for low density polyethylene. So temperature is increased from here to here. So the material remains more stronger, more stiff at low temperature. When you go to higher and higher temperature, the material becomes softer, and then the stress strain behavior can become very, very dependent on temperature. Okay. So, it is very important to know the operating temperature of the polymer will dictate its mechanical behavior. These two are not decoupled, these are not different things. Okay. And this is important because if you think about metals, typically metals have a very high melting point, 1000 degrees, 1500 degrees and so on so. But we actually use them at room temperature or maybe up to 100 degrees Celsius. So, we are actually far away from their melting temperature. So, the operating temperature does not cause much of a change in the physical behavior, the mechanical properties. But this is not true for polymers. For most of the polymer, the melting temperatures are like 100 to 200, and many times we may operate them under 70 to 80 degrees Celsius. So, we are actually 50% or 60% near the melting temperature. So, we have a huge difference on the mechanical behavior of polymer in a different temperature zone. Okay. So, even though we say metals and polymers can be used interchangeably, but the operating range of the temperature and the influence of this temperature range on the mechanical properties are far more influential in the polymers than in metals. Okay. So, we have to keep all this in mind, that the temperatures are very important in dictating mechanical properties of solid polymers. So, now the experiment I showed is called a tensile experiment, because we are actually putting a tensile force to pull. Okay. You can also do the opposite, it is called compression. Okay. You will take a material and you basically compress it. When you try to compress it also, you can measure the same stress strain curve, and you will see that depending upon whether you apply a tensile force or a compressive force, the stress strain behavior can be quite different. Okay. So, here this is again a polystyrene, which is a brittle or amorphous or a glassy polymer. So, under tension you can see that there is a linear region, and then it breaks at this point. Okay. There is no yield point, there is no ductile behavior, there is no strain hardening, it just breaks at certain point. Okay. So, it has a very small elongation at break because of its being a brittle material, and this curve is obtained by a tensile force. Now, you take polystyrene, but you apply a compressive strength. So, in this case you can see there is a, you basically come from you can basically see that there is a clear evidence of a yield point here. So, what happens is, because when you have an amorphous or a glassy polymer, the molecules are not arranged in a particular periodicity. Okay. There is going to be a lot of cracks, there is going to be some sort of a heterogeneity. When you try to pull, you see in the video initially some small hole happen, right. So, those holes can actually happen from a small defect within the material, and the tensile force basically amplifies those crack propagation and becomes easy for them to break. Whereas, when you try to compress, you do the opposite. Even if you have any defects, you are basically trying to compress it, and then the material behaves a little differently than compared to tensile force. Okay. So, when you look at stress strain behavior, you ask the question like whether it is based on a tensile force or compressive force, whether the material is going to undergo a compressive force or a tensile force. So, accordingly the stress strain curve should be obtained. If the material is going to be used under a tensile load, you better do stress strain curve based on a tensile force. If the material is going to be used under compressive force, you better get that stress strain curve from the compressive load. Okay. And you can see that there is quite a lot of difference between which way you do this stress strain curve. On top of that, temperature is also important, strain rate is also important. Okay. So, now the stress strain behavior typically shown by this kind of curve, and then we can read out all the information qualitatively. But many times when you try to compare material of different kinds, we need some sort of a quantitative information to compare between materials. Okay. So, this basically requires us to define some quantities, okay, some numerical quantities that we can compare with. Okay. So, then we define something called modulus of elasticity, okay, or different kinds of modeling. So, the most important one that you all might have familiar with is called the Young's modulus, also known as modulus of elasticity. This is usually represented by this letter E, is defined as stress divided by strain. In other words, this is basically the slope of this linear region. Okay. And this sigma here is a tensile stress, which is defined by force, tensile force per unit area, and epsilon is the axial strain, the strain in the axial direction. There can be a strain in the lateral direction also, but you do not count it in this calculation. So, here you are looking at how much stress is acting on this material and divide that by the axial strain, okay, the strain in the direction of the pulling. Okay. and usually it is given in megapascals, sometimes it can be also given in gigapascal. Okay. So, this Young's modulus or elastic modulus of elasticity is nothing but the slope of this linear region, right. Sometimes we also call this as there is something called initial modulus. It is basically the slope of stress strain behavior at the origin. So, if you look at the slope at the close to the origin, that is called the initial modulus, and there is something called secant modulus ES. This is basically a slope of a straight line drawn from the origin to any point on the curve in the elastic range. So, in a way the Young's modulus and secant modulus are the same thing. Okay. But secant modulus can also be used if you are away from this, if you are you can actually define it at any point along this line. And there is something called tangent modulus. This is the slope of a tangent to the curve at any point. That means I can go to any point on the curve and draw a line and get the slope of this tangent. Okay. So, it is basically going to tell you at that particular strain what is the modulus, elastic modulus of the material. So, these are different kinds of modulus that we use to characterize or differentiate between materials. And there is another thing called the flexural modulus. So, sometimes the material is under some sort of a bending load, okay, and you want to know how much it can resist bending. For example, if you are thinking about a PVC pipe, okay, and PVC pipe you want to use it for supplying water or something, and you will probably expect some sort of a load on the pipes, okay. So, you want to make sure the pipe does not bend too much, okay. So, a bending rigidity or the resistance to bend is actually measured through this flexural modulus. So, the way it is measured is you take a beam of the material, the plastic that you want to do, you basically support at two different ends, you take a particular length of the material, certain height, certain width, usually it is made into a rectangular block, support at two different points, and then you apply a load P at the center. Okay. So, when you apply, you are basically trying to bend it, you will see there is going to be some amount of deflection from its equilibrium point. If you look at the center of mass, it moves from here to somewhere here. So, that is a deflection, and this will depend on how much load you put, right. So, here in this operation, the flexural modulus EF is defined as P times L cube, where L is the length of this, basically proportional to this L, and then divided by 4W H cube and delta. Okay. And if you have a very high flexural modulus, it would mean it will actually resist bending. Okay. So, if you want to have a situation where you do not want to have too much of bending, you want to choose a material that has a very high modulus of flexural modulus. Okay. Then there is something called shear modulus. What we talked about in the Young modulus is based on the axial or the tensile force. Sometimes we try to shear a material, not pull it, but shear. You keep one side fixed and the other side is actually sheared. So, then the shear modulus is defined as shear stress divided by shear strain. Okay. So, that is called shear modulus. Now, there is also relationship between different modulus, especially between shear modulus, Young modulus and Poisson ratio. Poisson ratio is defined as when you try to have a strip and try to stretch it, apply a kind of a tensile load, the film will stretch in one direction and it can contract in other direction. So, you define Poisson ratio as a lateral strain divided by the longitudinal strain, and a theoretical limit is usually about 0.5 or it can be less than this. So, this Poisson ratio nu and the shear modulus, elastic modulus or the Young modulus and Poisson ratio, these are related by this particular relations. So, if you know two of them, you can find the other one. And there is another thing called a bulk modulus, which is actually nothing but the inverse of compressibility. So, as you know that compressibility is defined as dou P by dou V by dou P V naught, but bulk modulus is basically the inverse of compressibility. It is defined as dou P by dou V divided by V naught. So, once this definition is there, we can also relate the bulk modulus with your Young modulus as well as the Poisson ratio. Okay. And if you rearrange this, you will be able to show that the Young's modulus, bulk modulus and shear modulus, these are related. Okay. So, here is an example of various material and corresponding, this is Young modulus, and this is the fluxural modulus, and this is Poisson ratio, and this is called the yield stress. So, this is stress up to which the material is elastic and above which it is going to undergo plastic deformation. So, if you look at these these group of materials, okay, these are all metals, right, steel, bronze, aluminum, you can see that they have of the order of 200 gigapascal of Young modulus. Okay, this means these are very hard material compared to, if you consider the bottom ones, which are polypropylene, polystyrene, or ultra high molecular weight polyethylene with some fillers. You see that these are actually 2 orders of magnitude smaller than the metals. Okay, it already tells you in terms of strength of this material, in terms of Young modulus, steel or metals are quite 200 times or 2 orders of magnitude stronger than polymeric materials. Okay, and similarly, if you look at fluxural modulus, that means the ability to bend this material. You can see that again the metals have a very high amount of fluxural modulus, whereas the polymers have 2 orders of magnitude smaller. And Poisson ratio typically is very small for metals, but it can be very close to the theoretical limit for polymers. Okay, so that means when you try to pull this material, the contraction in other directions is actually quite a bit for the polymers compared to metals. And of course, there is also yield stress. Clearly, yield stress is also quite different between the metals and the polymers. In general, you can actually look at, suppose if you want to compare between nylon 66 versus let us say Teflon. Okay, let us say you want to make a product, you have a choice of either using a Teflon or nylon. Okay, so you basically compare what is the Young modulus of Teflon and nylon. Of course, nylon seem to withstand more tensile load, and then if you look at the fluxural modulus, they are not very different. That means they both have similar kind of a bending property, whereas if you look at the Poisson ratio, Teflon seems to be able to have a higher deformation, and then if you look at the yield stress, nylon seems to withstand a higher amount of load before it undergo plastic deformation. So, you can look at this kind of comparative analysis of material by looking at Young modulus, fluxural modulus, yield stresses, and Poisson ratio. Okay, so this is how you would probably compare different material, and the choose a material that you want to consider what load you want to have in your application, right. So now in terms of so whatever we talked about the stress and strain, these are all quantities. These are quantities that are defined, and there are quantities that we measure. Okay, the quantities that we measure through the kind of tensile testing machine that I showed, these are called engineering stresses and engineering strains. So, this engineering stress sigma is defined as Fi by A naught, where Fi is the instantaneous load divided by the area of the original sample. Okay, because the original sample area we know, the cross section area we know, because we give the dimensions, the thickness and the length and everything. Whereas the true stress is actually defined as the instantaneous force divided by the instantaneous area, but typically we do not measure instantaneous area as we try to pull the material. Okay, so what we actually measure in the tensile testing machine is the engineering stress, but the true stress is something else. Okay, it depends on how much the instantaneous area is different from the original area. Similarly, if you look at the strain is actually defined as the instantaneous length minus the original length divided by the original length, whereas true strain is basically the integral of dl by L. Okay, so dl is the differential amount of length change at any point time, and L is the instantaneous length at that particular time, and integrated over L naught to Li. So, this is more correct way of defining the strain, but for practical purposes, when we try to do measurements, we simply measure the instantaneous length minus the original length divided by the original length. Okay, so because of the practical reasons how we measure, we distinguish between engineering stress, engineering strain versus true stress and true strain. Okay, and we can also define another quantity called extinction ratio lambda, which is basically the ratio of instantaneous length to the original length, and then you can, so from here if you combine these two ratio, you can show that the extension ratio is nothing but 1 plus epsilon, where epsilon is the engineering strain. This is the engineering strain. So now what you can do is you can go to the true stress definition, which is the instantaneous force by instantaneous area. You can actually multiply this equation with A naught at the numerator and denominator. So now we can define this is the engineering stress and then multiply by this factor. So if I know A naught and AI and the engineering stress, we can get the true stress. Similarly, when you go to true strain, the definition is integral from L naught to Li dl by L, and then this will give you ln of L. When you put the limits, you will get ln of Li by L naught. And now you can also write this ratio little differently. For example, during this transformation, L is changing, A is changing, but the volume remains the same. So volume of the material has to be constant. So we say L naught A naught should be equal to Li AI. So that's constant. So you can show that the A naught to AI should be equal to Li by L naught. This is coming simply from the volume conservation. So then what we can do in this expression, we can replace Li by L naught with A naught by AI, or we can also write Li by L naught as 1 plus epsilon. So true strain has these three expressions possible. It can be written in terms of ln of Li by L naught, or it can be written as ln of A naught by AI, or it can be written as ln of 1 plus epsilon, depending upon whether you know Li L naught information, or you have A naught AI information, or you have the engineering strain information. Okay, so so again, coming back to true strain, we already noted that the true strain can be written as the engineering strain times A naught AI. Now we can also write A naught AI as 1 plus epsilon. So this is how all these quantities are related. So we got two sets of data. One is the engineering stress, engineering strain, and there is a true strain and true stress. Why this is important? Because when you actually make a measurement, you measure only engineering strain and engineering stress. When the material is actually under use, the actual load is actually true stress and true strain. If there is quite a lot of difference between the two, then we may actually design something that is not suitable for a given application. So therefore, it is important to find what is the true strain and true stress from these relationships. Okay, so I think I have an example of illustrating this point. If you consider this example 1, okay, so if I consider this example 1, so here the engineering stress measured is 10 megapascal, engineering strain is 0.2%, very small amount of strain. With this engineering stress and strain, let us calculate true stress and true strain. So as you can see, I am using this true strain as ln of 1 plus epsilon, that is this equation. Okay, I can use Li by L naught or A naught by AI. These are not given to me, only stress and strains are given to me. So I am going to use this expression. So you put ln of 1 plus epsilon, epsilon is 0.002. So ln of 1.002 is 0.0019. Okay. So if you compare this true strain and the engineering strain, they are not very different, they are very similar, okay, in this particular example. And then if you calculate the true stress based on the ratio of area, and then or since we do not have the ratio of area but we know the strain, we apply that true stress is equal to engineering stress times 1 plus epsilon. True stress is 10 megapascal, 1 plus epsilon is 1.002, so you get 10.02. So engineering stress is 10 megapascal, but the true strain is 10.02 megapascal. But still in this case you can see both the true stress and true strain are very similar to engineering stress and engineering strain. Okay. And then if you go to the next example, let us say I have another material where I have the engineering stress of 50 megapascal. Here I have a little higher strain, I have 1% strain. In the previous case we have only 0.2 strain. When I say 0.2 strain, it means you have pulled the material 0.2% of its original size. When you say 1%, it is little higher. Again you calculate the true stress and true strain, same formula. So here you see that in this case also the engineering strain and true strain are very similar, and the engineering stress and true stress are little different, but not very much. It becomes more important when you go to a very high strain like 10%. When you go to very high strain like 10% for a material having 100 megapascal, you see that the true strain and engineering strain are a little bit different, but you see the difference between the stresses. The engineering stress and true stresses are quite different. So that means what we try to conclude from here is, if you have a material which is more stiffer, what is the Young modulus for this case, do you think? What is E here? So this is 10 by 0.002. So that is basically about 5000 megapascal. So when you have a material that has a very high Young modulus, you see the engineering strain and true strain, and engineering stress and true stress are not very different. Whereas when you look at this material, so here the Young modulus would be 100 by 0.1, which is actually 1000 megapascal. So this is actually 5 times less stiffer. For this material, when you go to larger strain, the difference between true strain and engineering strain is quite different. Okay, so you should be able to use the measured engineering stress, engineering strain, and based on that you should be able to calculate what is the true stress and true strain. As long as your material is very strong, very stiff, this difference will not be very different. But for polymers and rubbers and flexible materials which has a lower modulus, which may undergo a lot of strain, then this difference become more and more pronounced, right? So that you need to keep in mind. Okay, so I think that's all I have.